Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain the paper Speech2Vec, a sequence-to-sequence framework for learning word embeddings from speech. This was published in Interspeech 2018. This paper is by Yuan Chung, James Glass from MIT CSAIL lab. So the tutorial is going to cover the overview of the paper. Then we will see what is the approach they have introduced in this paper to learn speech-to-vec embeddings. Then we will see what is speech-to-X, how the training is done, what is the architecture. Then we will see the difference between speech-to-vec and word-to-vec. Then finally we will see some experiments and results. So the overview of paper is, this paper is written to generate embeddings from speech. Basically those embeddings are word embeddings, but these word embeddings are not learned from the word or text data. They are learned directly from speech. You can think of this as speech version of word-to-vec. And this algorithm is designed to learn fixed length representations of the words, to learn this fixed length representation of the words directly from raw audio, which those embeddings will capture the semantic information about the words. And this paper uses encoder decoder framework, just like in sequence-to-sequence models, which uses recurrent neural network, and also it uses some inspiration from skipgram and continuous bag of word models, which are from NLP domain. Then as I said, these embeddings are learned, or these embeddings represents the semantic information about the word. But not only the semantic information about the word, like in word-to-vec, they also capture some other information. And we will see the difference between the word-to-vec and speech-to-vec in the coming slides. And this paper shows learning embeddings from speech gives better results compared to learning embeddings from the text. So the approach is like this. So basically what we want is, we want a model which is like word-to-vec, but we want to learn it from speech, not from plain text data, because text data will not have the information about the speaker, it will not have information about the channel in which the speech is recorded. So basically they think getting word-to-vecs or getting embeddings for words from audio should give better results compared to word-to-vec, because the speech will capture this, or the embedding should capture this speaker's information and channel information. So the goal of this paper is basically to get a fixed length representation for variable length audio sequence. So the variable length is because the words are speech segments, and speech segment for every word can length of speech segment for every word can vary, because it's audio, it's a time series. Then to encode those kind of variable length inputs, they use a recurrent neural network, and the output should also be a speech sequence, because as we know in word-to-vec, we try to take some word and try to predict some other word. Like for example, we try to feed one input word as an input and try to predict the context words, right? So just like that in speech, or in this paper, we want to feed a speech input which is a word, and we try to predict the contextual words which are also speech segments. For example, if I have a sentence, go to school, so if I take the word to, I want to predict go and school, but not in text. I want to predict them in speech, because so that is the whole idea of this paper. We want the speech as input and speech also as output. So now we'll see what is speech-to-vec. Speech-to-vec, the algorithm or the model used in this paper. Basically, they have built two different models. One is called a skipgram based speech-to-vec model, and another one is called continuous bag of word speech-to-vec model. We will see the difference between these two models, and we'll see which one is better at the end of this tutorial, because I'll show you some results. So speech-to-vec and speech-to-vec, a skipgram based speech-to-vec model is like this. We have let's assume we have 3-word utterance, where we have xn minus 1 is a word which is a speech segment, xn is a middle word which is also a speech segment, and n plus 1 is also another word which is also a speech segment. So what I want is, I want to feed this xn as input and want to uh, perfectly predict xn minus 1 and xn plus 1. So as we know, this should be the input, xn should be the input, and xn minus 1 should be the output. So xn is a raw audio. We can feed this raw audio directly if you use let's say convolutional neural network or some sort of 1D convolution kind of thing. But here they are converting this speech segment raw audio into feature sequence, which are MFCC features. We will see the dimensions of these MFCC feature later. So xn is an input sequence, which is a sequence of feature vectors x1, x2, xt, and I want to feed this feature sequence as input to some RNN, and whatever I get at the end of the last hidden layer, last hidden representation ht is my embedding. So this embedding Zn will try to predict this xn minus 1 and xn plus 1. So here we are taking this Zn and feeding it to another neural network or the recurrent neural network, which is called a decoder. And this decoder is also an LSTM which tries to predict from this Zn, tries to predict the xn minus 1 feature sequence. So the yn minus 1 is a feature sequence here from this, which should be similar to xn minus 1. So what we want is, after training, once we feed this as input, we want this yn minus 1, which is this feature sequence, should be similar to xn minus 1. And we also feed this Zn to another projection layer, which is again a recurrent neural network which tries to predict another feature sequence, which is yn plus 1, which is the next word. This is the previous word, this is the next word, and all I want is, I want to accurately predict xn minus 1 and xn minus 1 and xn plus 1 given xn. So, and to train this model, we can directly use mean square error as the objective, or mean square error as the loss function, and optimize this network using optimize this network using that loss, which is a root mean square error loss. So that we can do it for the entire speech corpus, and finally we can train a nice neural network, a nice model, which will give us, when we feed this word xn, which will give us this embedding Zn, which is similar to the Word2Vec, that means which should capture the semantic relationship about the word, right? So that is the whole idea of Speech2Vec using skipgram model. Now we will see another model which is called continuous bag of word model for Speech2Vec. So here what happens is, we try to feed in this you can see we are feeding the middle word as input and try to predict the context words. But here the idea is, we want to feed the context words as input and try to get the middle word as the output. So here again we have, let's assume we have this example, we have 3 words. I want to feed xn minus 1 and xn plus 1 as input to the encoder, and the decoder should be able to predict the xn, which is the middle word. So this is left word, this is right word, and I want to predict the middle word. Now we can ask me the question, where is the embedding or speech embedding? So the embedding will be obtained by adding the last layer or last hidden representation, which is ht of n minus 1, which takes xn minus 1 as input, and ht of n plus 1, which takes xn plus 1 as input, and tries to sum them, and that is going to be my Word2Vec or Speech2Vec vector, which will have the semantic information about the word. So that is about Speech2Vec model. Now we will see the difference between, we will see the accuracy, or we will see the performance of Speech2Vec using skipgram and Speech2Vec using SIBO model later. But we will see what are the difference between the Speech2Vec model and Word2Vec model. So in Speech2Vec, as we know, we try to find, or we try to generate a fixed length word embeddings or fixed length embedding vectors directly from audio, which will capture the semantic information, just like in Word2Vec. But if you think of Word2Vec, in Word2Vec, if you see, we try to feed the words, one-hot encoding of the words as input, and try to predict the one-hot encoding of the words as output. So the input dimension to input dimension in the case of Word2Vec is fixed, so we can directly use a fully connected layer or feed-forward neural network to feed the words as input and try to predict the words as output. So that is the difference between unlike Word2Vec, we have variable length inputs and variable length output. That's why we need recurrent neural network. So the difference between Word2Vec and the Speech2Vec is Word2Vec uses fixed fully connected layer or a feed-forward neural network kind of networks, but Speech2Vec you should be using this networks which will capture the temporal information, which is like recurrent neural networks. And the most important point is Word2Vec, if you see, the word embeddings for every word will be fixed. What do you mean by that? If some word, for example, if I say if there is a word like tree, the embedding for that word will be fixed. So you can create a dictionary kind of thing for all your words in your language. After you learn these word embeddings, you can keep this as a dictionary. Like for every word you have this corresponding fixed length vector. But in speech it does not work like that, because speech, for example, let's take a word drum, can be spoken by multiple people. For example, if I speak the word drum, it sounds different because the voice characteristics of the person is different, which is again speaker information. And if someone else says it in different, if someone else says the word drum, his voice characteristics are different. So the embeddings which we get for every word in Speech2Vec model can be different based on the speakers, and also it varies based on the channel. For example, if you record that word in a studio environment and get the vector, and if you do the same recording using some telephonic channel and do compute the word embeddings, those two will be different. So we will see how different those vectors are going to be, and how to get fixed length representation, uh, uh, and we'll see is like how much variation is there for every word based on the number of speakers and all those experiments later. So basically what we try to say is word embeddings generated using raw text data is a fixed or is a deterministic features, deterministic embeddings, but speech embeddings or Speech2Vec embeddings what we get in using Speech2Vec may vary based on the speakers and channels variations. Now we will see some experiments. And the experiments will see what are the data sets used and what is the input features and stuff like that. So 500 hours of data, 500 hours of LibriSpeech data set is used, and that 500 hours of data will have 1252 speakers. So this is basically a subset of LibriSpeech data, which is 1000 hours of data, and this data is studio recorded, or it's also called broadband speech data. So this data is a speech recognition data set, and the input to the network what we are using is going to be 13-dimensional MFCC feature, which is going to be fed to the recurrent neural network during training, and these features are computed for every 10 millisecond window. And as we know that this speech data, if you look at this LibriSpeech speech data, it has the speech sentence and its corresponding transcript. But what we want to train this model is word by word speech segment. So this is not available in the actual speech recognition or actual LibriSpeech data. So what we want is we want to get this word boundaries. For this we can use this forced alignment technique, which is again one speech recognition model, which will give us word level boundaries or even phone level boundaries. And because we have this ground truth text data, we can align this speech along with this ground truth text data and get word level segmentation. So this word level segmentation is used. After we do this word level segmentation, we get data set which will have words and corresponding speech segment of that word. So that means like word by word we'll have the speech sentence, word by word we'll have the speech segments. So once we get that kind of data, now we can construct our model, because we have our encoder decoder model, which is a which is sequence to sequence model. We have encoder, which is a single layer BLSTM, bidirectional LSTM, and we have a decoder, which is single layer unidirectional LSTM. So decoder is unidirectional, encoder is bidirectional. And the window size used, window size basically the number of words to the left and number of words to the right you want to predict. Basically, you like how many words you want to predict. Predict in the sense, as we see here, we have three words here. This is the middle word, left word, and right word. So this algorithm is not designed only to predict one word to the left and one word to the right. You can actually make more words like 3 or 4 words to the left and 3 or 4 words to the right. So that length or window size used here is 3, and learning rate is 0.01, and model is trained using the model is trained for 500 epochs. And I'm not this point 5 the point number 5, I'm not completely sure. They are saying window size k is 3. I'm not sure if they are meaning the number of words they are trying to predict is word 3, or is it this entire this considering this entire window size as 3. I'm not completely sure about that. Maybe it's if they say window size k 3, maybe they are meaning total number of words 3. Not completely sure about that. So the learning rate is 0.01. Model is trained for 500 epochs. Now we'll see some results. They have done a lot of experiments which are very nice. You can read the paper. I'll try to explain all the experiments they have done here. Very, very nicely written paper. Explains or gives very good intuitive idea of why these kind of things are happening. So basically, they have this benchmark comparison of word-to-vec models. So they have this word similarity matrix. They have around 13 word similarity metrics, and they have done this experiment for the SIBO speech-to-vec model. SIBO is basically continuous bag of words model, and they have the skipgram speech-to-vec model, and have also tried to do the same thing using word-to-vec. These word-to-vecs are learned using the text data of this 500 hours of data. They have not taken the general word-to-vec embeddings, which are like glove embeddings, which you can see trained using common crawl data kind of thing. But they have used this 500 hours of text data, whatever 500 hours of data, then the corresponding transform what they have used that text data itself to generate these word embeddings, and they have compared this speech embeddings they have generated along with these word embeddings. And they have 4 different model here. You can see speech-to-vec SIBO is speech-to-vec model, uses continuous bag of word trick, and skipgram trick with speech-to-vec, word-to-vec trained with SIBO, and skipgram trained with SIBO. So they have 13 word similarity benchmark experiments they have done. So basically what you can see is this vector dimension basically tells you the dimension of the word embedding, dimension of the speech embedding here, and dimension of the word embedding here. As you can see, it varies from 10, 50, 100 and 200. So as you can see, the whatever is marked red here is actually the best model among these 4 models. But whatever is marked in dark here is the best model among the within this model with these many the size of with respect to the size of the embedding. So as you can see, this is actually beating all like 8 out of 13 tasks, or 8 out of 13 word similarity benchmarks are dominated by this skipgram speech-to-vec model compared to these others. Only 4 or 5 of them are obtained. 4 of them are taken by this word-to-vec skipgram, and 1 is by this word-to-vec SIBO. So basically this shows you that this model is actually, the speech-to-vec is actually working better than this word-to-vec. But I'm not sure what is going to happen if they take the general word embeddings, which are like trained on thousands of it's large amount of text data. But if they do word embedding training with whatever 500 hours of text data they have, 500 hours of transcriptions, they get better system using only skipgram speech-to-vec model. Now the second experiment they have done is they wanted to see how this the amount of data helps, or how this amount of data plays with this word embeddings performance. So they have around here they have, I think they have only 6 word embeddings, 6 word similarity tasks here, word similarity benchmark tasks here. They have the amount of data they are using varies from 10 to 100. They vary with size of 10%, 40%, 70%, 100%. And as you can see, actually, basically, I forgot to tell you one more thing. These numbers are basically Spearman's correlation coefficients. So basically, they compute this correlation between this word similarity ranking generated by this algorithm along with human rankings, and the correlation basically tells you, the Spearman's correlation coefficient tells you like how good they are, right? So these numbers are those Spearman's correlation coefficients. And here also you can see if they vary, as the amount of data varies, as the amount of data increases, then they get better results, or they get better correlation results. And here again, uh, this model is again kind of working better than any of the other models, like out of these four. Now, finally, we will see some results on the variations in speakers, and we will see some visualization here. So basically, as I said, in Speech2Vec, the word embeddings or the speech embeddings varies, or speech embeddings changes based on speakers. If somebody says the word Trump, and the whatever the word embedding you get or speech embedding you get may not be similar to some other person says the word Trump. So basically, what they have done here is they have done this experiment where they have got this standard deviation for four different kinds of parts here. So basically, they have taken words which are occurring around 5 to 99 times in the corpus, and they have taken words which are occurring 100 to 999, and they have taken some words which are occurring 1000 to 10,000, and they have taken also some words which are occurring more than 10,000 times. So basically, they are generating so they are obtaining this standard deviation of each dimension of this, let's say, 50 dimensional vector within this words which are falling within this range, which means if some words which are falling, or which some words which are occurring less than 99 times, they are taking those words and trying to compute the standard deviation of each of the dimension within that words, and they average these standard deviations for all the words, and they get whatever they get here is those numbers. So the average standard deviations for SIBO, using or considering only these words which are falling within this range, is actually lower compared to skipgram model, which is kind of weird. But as you can see here the number of words here, if number of words are occurring many times, or number of instances of that word is occurring many times, which is like more than 10,000 times, the skipgram model, the standard deviation of this, or the variation of this skipgram model, is better than the variations which are happening inside SIBO model. That means the skipgram model is much better than SIBO model, even if when we consider the speaker characteristics, which means, like, if you consider some words, I mean, although as we said, the words spoken by different people will have different embedding, but if that word is occurring many times in the model, averaging all of those embeddings and getting a final word embedding will be much better compared to the SIBO, the same thing done by SIBO. So that is a nice figure, and that's a nice experiment, which is like averaging all the word embeddings of the same word occurring many places by many speakers, and getting a final word embedding of that particular word, which case is like kind of removing all the speaker characteristics. And they show the skipgram works better in that case. And at the end, we'll see some results, visualization, which is like similar to the word embeddings visualization, as you see. So as we know that the words which are semantically similar will cluster together, as we know in word embedding, word2vec. So you must have seen these kind of pictures when they published this paper back in 2012. They showed that the words which are semantically similar will cluster together. Like, for example, the word king, queen, man, woman, those kind of words will cluster together, means the word embeddings will cluster together. The same thing happens in Speech2Vec also, where they have this magnificent, wonderful, these kind of beautiful, lovely kind of words are clustering together, as you can see this green thing. And some words which are like bad words, like disgusting, ugly, horrible, those words are clustering together in some other cluster. So this is kind of nice, as we know, this is kind of nice, which is like similar to Word2Vec model. And thank you so much for watching this video. If you are not subscribed to my channel, please subscribe for more videos, and see you in the next video.